This presentation is on adjoint-based shape optimization applied to inkjet printheads. It was work done by Peter Kungutsev, who was supervised by me, Matthew Juniper, as part of an ITN SSE MID, Stability and Sensitivity Methods for Industrial Design, funded by the European Commission. A detailed description of this work can be found in the Journal of Fluid Mechanics, Volume 871, and in this presentation I'll talk about the main highlights of this paper. I'll start by describing an inkjet printhead. On the right here you can see a picture of an inkjet printhead. The width in this direction is a few centimeters, and inside these black bits just here there are many small channels running in this direction. Each of those has a small nozzle, it's so small you can't see it, and upstream of that nozzle is a piezo-electric crystal, and when a voltage is applied to the crystal it changes shape and squeezes a drop out through the nozzle. In this presentation we're going to look at a very simple generic geometry, and this is known as thin film technology, in which the piezo-electric crystal sits just above the nozzle. Ink is pushed in through the inlet and sucked out through the outlet. It moves slowly along the channel and then from time to time is pushed out by this piezo-electric crystal. And there are two Reynolds numbers in this problem. The first is that of the through flow, which is around 0.1, and the second is that of the oscillating flow, which is around 0.01. And the exact definitions of those Reynolds numbers are given in the paper. So here is a very simplified cartoon of the droplet ejection process. On this axis here we have time in microseconds. On this axis here we have voltage applied to the piezoelectric crystal. So we apply a voltage for say 5 microseconds, and this causes the piezoelectric crystal to bend. This forms acoustic waves within the channel, and these push out a jet of ink which then turns into a droplet. After that droplet has left, there are now some acoustic reverberations within the channel. And what you can do, although you don't have to, is try a pulse in the opposite direction to pull the piezoelectric crystal upwards to try to get rid of those reverberations, and then you can try another signal, etc. And these residual oscillations are actually quite a problem because they affect the subsequent droplet. For example, you try to eject another droplet before these residual oscillations have died away, then the droplet you eject will be bigger or smaller depending on the exact timing of the pulse relative to these residual oscillations. And it's important in inkjet printing that each of these droplets is the same, otherwise the image becomes fuzzy or contains streaks and lines. So the first question we asked ourselves was, how can we change the shape of this jet boundary here in order to make the residual oscillations die away more quickly without affecting the pressure drop of the through flow. And this is rather a curious problem because it's a viscous acoustic problem. It's curious because in most acoustic problems one ignores the viscosity, but in this case the mechanism that is killing off those oscillations is the viscosity, so you can't ignore it. Nevertheless, the problem becomes much simpler if you divide it into two problems. The first is for the steady flow, and here you say, let's look at an incompressible, i.e. no acoustics, an incompressible steady flow with no oscillations. And that's for the through flow, and for that we use the incompressible Navier-Stokes equations, and these are relatively easy to solve. And then the second problem is for the oscillating flow, and here we say we have no steady flow, and we look at acoustic wave propagation. And here we have to include the viscosity and also the thermal diffusivity. And we ask, is it possible to change the shape of this microchannel in order to maintain the pressure drop required to flush ink through the channel while damping these residual acoustic reverberations as quickly as possible? And so we define two objective functions, one for the steady flow, which is the viscous dissipation in the steady flow, so we have the gradient of the velocity field here squared multiplied by the viscosity, and then we integrate that over the volume. And the other cost function is the oscillating flow's decay rate, and this introduces the variable S, and this is what's known as a Laplace variable, and it's the variable in the Laplace transform that says that the pressure, for example, as a function of space and time, can be expressed as a shape in space times e to the power of s times t, where t is time. And s is a complex number, and the real part of s is the growth or decay rate, and the imaginary part of s is the frequency of the oscillation. To summarize, we have an objective function, which is that we want to change the shape such that s is as negative as possible, which implies a large decay rate, subject to the constraint that the viscous dissipation in the new geometry is less than or equal to the viscous dissipation in the original geometry. So let's turn now to the steady problem, the constraint. On the top here we see the direct velocity field. This is actually the modulus of the velocity, the absolute value of the velocity. So the flow is coming in from this manifold here, going round the corner, speeding up because the area changes, it gets smaller, going out of this side here and slowing down as it goes into the outlet manifold. And the flow rate through the nozzle is negligible compared with the flow rate going across it, so we set it to 0 here. For this optimization procedure we use adjoint-based gradients, and that means calculating the adjoint velocity field, which we call U-bar dagger. And this has a physical meaning. It's the sensitivity of our cost function, the viscous dissipation, to external forcing of the momentum equation. In other words, if we were to magically add some momentum somewhere in the fluid, we'd find it would have most influence on the viscous dissipation around these corners here. And then we can work out the sensitivity to boundary changes from a combination of the direct and the adjoint velocity fields. And the details of that are given in the paper, but as you'd expect, geometry changes that change the flow around these corners here have most influence on the viscous dissipation. And now we consider the viscothermal acoustic problem. Now with a slight transformation this problem becomes self-adjoint, which actually makes it easier to solve. And what we're showing here is the velocity eigenmode. It's the u hat of x if the velocity field is u hat x e to the power of st, and this is actually the absolute value of that. And so think of these simply as the natural frequencies of this channel. And these have therefore a frequency, in this case written in kilohertz, and also a decay rate. So we find the one in this case with the lowest frequency, which is this one here, and it has a decay rate of around minus 17 kilohertz. And the plot we see here is the eigenfunction corresponding to that decay rate and frequency combination. And this picture, as well as being the direct eigenmode, it's also the adjoint, so it shows us where the decay rate is particularly sensitive to changes in u hat. And so the decay rate of oscillations will be particularly affected by changes to u hat that occur around these corners here and also around the nozzle. So now we take our generic geometry and we parameterize it, which means that we represent it by a series of points, and then we use our adjoint methods to say if I were to move one of these points in one direction or another, how would that affect, firstly, the viscous dissipation of the throughput, which I want to keep constant, and secondly, the decay rate of the oscillations, which I want to make as negative as possible. And in the chart on the right, as a function of iteration in our optimization process, I'm going to plot in orange the viscous dissipation of the throughput, and in blue the decay rate of the oscillations. We see that the computer moves the points around until we are really constraining the flow around the corners here, while opening up the channel in the middle. And so we can see that this increases the acoustic decay rate, while, in this case, keeping the viscous dissipation to be less than or equal to its original value. This was done by the computer. The physics is programmed into the computer, but the computer doesn't understand, of course, what it's doing. Humans, however, can add the physical interpretation of this. So physically what's happening is that the flow is constricting where the acoustic velocity is large, and this increases the viscous dissipation of the acoustics. But this also increases the viscous dissipation of the throughput, so to compensate, the computer opens up the channel in the middle, such that the total viscous dissipation of the throughput is unchanged, but the viscous dissipation of the oscillation is increased. Now in this case, we actually constrained the nozzle shape to be the same, but the nozzle shape itself has an enormous impact on the viscous dissipation rate. And I should mention that we also constrained this part of the nozzle, bottom and top, to be flat. So let's just watch that again. And we ended up with rather a funny shape. An inkjet printhead manufacturer would have many different constraints, and the moment you add those constraints in is during this optimization process. We gave ourselves a lot of license here to do what we wanted, but this is nonetheless a nice demonstration of a proof of concept. I'm just going to sum up the main points. Firstly, to make the calculations much faster, we separated the flow inside the printhead microchannels into a steady flow with no oscillations and an oscillating flow with no steady flow. And that's done formally in the paper, which shows that it's allowed if those Reynolds numbers are both small. For the specific optimization problem here, we set the viscous dissipation of the steady flow, and we say to the computer you mustn't end up with a bigger viscous dissipation than that, and then we try to increase as much as possible the decay rate of the acoustic oscillations. We then parameterize the geometry of the inkjet, and we work out how each of these two functions here is affected by each of the parameterizations of the geometry, and then we use a gradient-based optimization algorithm to optimize the shape such that we maximize the decay rate of oscillations while keeping constant the viscous dissipation of the steady flow. And the optimum shape we came up with here has a 40% larger decay rate and a lower pressure drop. Now that means the larger decay rate means that you could print droplets with a higher frequency, and you wouldn't have to change the pumps pushing the ink through the inkhead. So having done that for the geometry, the next step is to take a fixed geometry, and it could be the existing one, and see how we can change the waveform in order to kill off residual oscillations with the piezo-electric crystal itself. And that's in another paper. So I'll stop there and just go back to the title page. This work was done by Peter Kungutsev under my guidance, Matthew Juniper, funded by the European Commission as part of SSE MID, which is a Marie Curie ITN.